The pulley's radius of the pulley. Let's give that a radius of 12 centimeters. Not too large, large enough. Now here's the thing, we of course are going to have a question we have to try to answer. So when released, M1 falls and hits. If M1 hits the ground, with a speed of 1.8 meters per second, then what we want to know is, what is the pulley's mass? So right away you can see that, well, okay, I'm not just going to be able to take this form of the equation and plug stuff in and get a velocity. It's sort of the other way around, right? But we'll work this out. First, okay, so I want to make sure I identify, I'm looking for mass of the pulley. Mass of the pulley is my unknown. Fair enough. Strategy here. Well, I'm going to use conservation of energy. There's gravitational potential energy here. There is initially no kinetic energy anywhere. And when M1 hits, well, everything will have kinetic energy. 1, 2, 3 things will have kinetic energy, right? But M1 will have lost all of its potential. The thing is, M2 will have gained potential. So when we line up our initial and our final situations, we have to account for all of those things. So here's what this looks like. Start it out, and I'll have to expand this as I go. Mechanical energy initial is equal to mechanical energy final. Easy enough. So my kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Cool. Initially, kinetic energy. Well, nothing is moving initially. It's released from rest. Right? So this entire thing goes to zero. But you want to remember that there are 3 things that could have kinetic energy. They don't initially, but they could. So this initial kinetic energy is made up of a sum of 3 kinetic energies, which is all 0. This potential energy, it's in the form only of a position for mass 1. So we have mass 1, G, H. And you could write a Y there for H, same thing. Now here's where we have to be more careful. The final kinetic energy. Well, when M1 hits, 3 different things are moving. M1 is moving down, M2 is moving up, and pulley is rotating. So I have 3 things I have to write in here. The nice thing is, I recognize that M2 and M1 have to be moving at the same speed. They're tied together, they're connected objects. So since they're moving at the same speed, the kinetic energy of those two can be M1 plus M2 times their final velocity squared, right? So those two are moving at the same speed for those two. And now there's a term, I'm going to run out of space here, I'm sorry. There's a term for the kinetic energy of the rotating pulley. Well, I'm going to sort of do this. I'm going to add, and I'm going to just extend this down here. Kinetic energy of the rotating pulley. Well, that will be 1/2 times the moment of inertia of the pulley times the angular velocity of the pulley squared. All right, so that's kinetic energy of a rotating object. Cool. The pulley is not translating anywhere, so there's no extra bit to this kinetic energy right here. That's it. But finally, there is some potential energy. I have 3 terms of kinetic, and I have potential. M2 will end up higher. So, M2G. Now, how high will M2 go? Well, it's going to, since it's connected to M1, it's going to lift up by a distance of h. H, right there. And again, if I use y here, I use y there, it's the same thing. Wow, so I have a little bit of a busy equation. And I have to keep in mind the ultimate goal. I want the mass of the pulley. So mass of the pulley, there's M1, M1 and M2. M2, where's mass of the pulley? Mass of the pulley turns out is hidden in here, in this term. So I gotta kind of wrangle some stuff out of it. I'm also going to use a relationship that's going to help me reduce the number of variables that I have to remember, have to deal with here. That relationship, if you recall, is just this one. Velocity is equal to, where'd my strategy go? Okay, so, sorry, it's equal to that. Or, this is really the substitution that I'm interested in doing. The angular velocity is equal to velocity divided by radius. I'm going to use that instead of that omega right there. I'm going to use, that's going to go right there. And so I'm going to try to write this all on one line and get rid of extra stuff, and we'll begin the process of simplifying. So here we go. Don't have to rewrite to 0. I'm going to write M1 GH, and my equal sign is going to be way over here on the left, and I'm just going to try to line everything up here. 1/2, so it's nice and clean. M1 plus M2 times that velocity squared plus, now, okay, moment of inertia of the pulley. I'm gonna write this term. So I have the 1/2. But what is the pulley? It turns out the pulley is going to be a solid disk. So that's very straightforward. Now, the moment of inertia of a solid disk or solid cylinder, right? 1/2 mr squared. So instead of writing I, I'm going to write 1/2 mr squared. Now, what m is this? This is the mass of the pulley. Aha, there's the answer I'm looking for, 1/2 mr squared. So I took I, and it's all this. Now, I'm going to do this substitution here, V over R for that omega. That quantity is squared. Sorry, it's getting a little close to that line. And now I have this final term, M2 GH, right? So essentially, I'm going to try to hide what's not critical there. There we go. Essentially, that's what I have to look at and solve. And my unknown is mass of the pulley right there. So I'm going to try to show you isolating that guy. Let's work on that. I'm going to begin anew here. And so, I look at this and I say, okay, I'm trying to isolate this. I will have to subtract that term and that term from both sides, and then I'll have to divide by a bunch of stuff to isolate that. So on the left, I started with M1 GH. I'm going to subtract M2 GH, and then I'm going to subtract this business. And that looks cool because I can actually factor out the GH, and it will simplify a bit. So subtracting the other term, this business, from both sides, 1/2 M1 plus M2 times V squared. And that has left me with this isolated. Now, I can simplify this a little bit. You probably already recognize a few things. That's going to go to 1/4. I have r squared, and I have r squared in the denominator. Those will cancel. That's curious. That's nice. So over here, it goes to 1/4, and I end up with mass of the pulley times V squared. Remember, r squared canceled, and that went to 1/4. That's what I have here, 1/4, and r squared is gone. So it's starting to look better already, right? I'm going to multiply both sides by 4, and I'm going to divide both sides by v squared. Oh, by the way, it is the same velocity in each of these locations, but it's not going to be advantageous to try to cancel it out. It'll just, if you try to cancel that, it'll creep up over here. So let's not bother. Multiply both sides by 4, and then dividing both sides by v squared. So, and I can simplify this as well. This is m1 minus m2 times gh minus 1/2 m1 plus m2 times velocity squared. So I've multiplied by 4, and I now divide by v squared. All over v squared. And that is equal to the mass of the pulley. I can work with that. So I'm going to substitute some numbers in. M1 is 5 kilograms, 5.0. M2 is 3 kilograms. G is 9.81. H was 0.75 meters. M1 plus M2, so 5.0 plus 3.0. V squared, I know the velocity was 1.8 meters per second. And that's squared. I don't know why I just wrote the units, but had been trying to save space by not writing units out. These are masses. That's acceleration. That's a height. These are masses. This is a velocity. Okay, but don't lose track of that exponent. That is such a common mistake. Lose track of an exponent. And this is over 1.8 squared. Don't lose track of that exponent either. Mass of the pulley. So it turns out we get an answer. Mass of the pulley. 2.167-ish, right? After some rounding. Well, because of sig figs, check this out. Some of the numbers with the smallest number of sig figs are your masses, and also this height. And this velocity, by the way, they all only have 2 significant figures. Let's round the answer to 2 sig figs. 2.2 kilograms. There it is. So what started out looking like a simple problem, we just wanted to know the mass of the pulley by analyzing motion of this system. At first simple, looked like it grew into an enormous nightmare of a problem, and then turned out it shrank back down to what you might call a modest, very manageable kind of problem. No big deal. So that is how we could apply this. One example that we could use. Oh, by the way, I didn't mention to you, this example itself comes out of your textbook. Let me give you the page number if I can find it. Okay. This comes from page 327. This is number 70. Just for your reference. So that's it for now. Thanks for watching. I'll catch you next time.